So in the previous video, we talked about several different types of acid-base neutralization reactions. And the term neutralization can be a little bit misleading because if you were to conduct one of these reactions and you were to, quote, neutralize the reaction, it almost implies that the resulting solution would have a pH of 7 because that's what we consider to be a neutral pH, all right? The thing is that the salts, when you conduct a neutralization reaction, we're always going to make a salt, all right? But the thing is that salt might or might not be what we generally consider as neutral, or meaning a pH of 7, all right? Sometimes the pH of the neutralized solution could be 7, sometimes it might not, all right? In this video, we're going to talk about why that is the case, all right? So first of all, are there examples where you would have a completely pH neutral or a pH 7 solution when you're done with your neutralization? All right, the answer is yes. That's going to be the case whenever you neutralize a strong acid with a strong base, something like hydrochloric acid with sodium hydroxide. All right, and the reason for that is has to do with what you have when you're done with the neutralization. All right, so this would be the reaction right here. When we neutralize these guys right here, we're going to end up having essentially a saltwater solution, meaning literally like what most people think of as saltwater, sodium chloride dissolved in water. All right, and the pH of that resulting solution would be a pH of 7. But the reason for that has to do with a little bit of what we talked about before. All right, so remember that there's this relationship between the Ka, or the strength of an acid, and the strength of its conjugate base, all right, and vice versa. All right, so we know that the Ka of an acid, which gives an indication of how strong that acid is, and the Kb of its conjugate base, which is the strength of the base, those things multiplied by each other always add up to the acid, the dissociation constant for water. All right, so what that means is that the stronger the acid, the weaker its conjugate base. All right, so the thing is, in this particular reaction, we know that hydrochloric acid is a strong acid. So what that means is that its conjugate base is an extremely weak conjugate base. All right, so when you have this this ion swimming around in solution, when you're done, it would have no inclination to want to pull an H plus away from water, which is what a base would want to do. It's just going to simply be an ion that is harmlessly swimming around in the water. All right. Same thing could be said about sodium ion. It is not going to act as an acid. All right. So since this doesn't act as an acid, and this isn't going to act as a base, neither of them would have any effect on the pH of the solution. All right, so that's why the resulting solution is going to have a pH of 7. All right, so why does it have a pH of 7? Well, there's still tons of water around in that solution, and that water is going to undergo that same self-ionization of water reaction that it always does. That leads to why water normally has a pH of 7. So the same thing's going to happen if you have a saltwater solution. All right. That being said, there are cases where the pH is not going to be 7. All right, so the case where that's not going to be true, the first case that we're going to look at is when you neutralize a weak acid with a strong base. All right, and the pH of this neutralized solution is not going to be 7. All right, so first of all, let's take a look at an example of this type of a reaction. All right. We're going to do acetic acid with sodium hydroxide. All right, and so when you conduct this reaction, all right, assuming we have one of this, and for every 1 mole of this, we're going to end up making a solution. We're going to make a salt. All right, remember we always make a salt and water. All right, and so water gets formed, but the salt that gets made is going to be sodium acetate. All right, and the reason that I drew it as two separate ions here is, remember, when you're done with this, it's going to be dissolved in water. And when it's dissolved in water, it's going to act as, it's going to exist as its dissolved ions. And so what I hope to convince you of is that determining what the pH of this resulting solution is actually goes back to something that we talked about a while ago, all right, which is determining the pH of when we have a conjugate base of something that we know, if we know something about the acid from which it came. All right, so what I want to start with is just a little bit of a mental exercise. Let's say that we fully neutralize this. We added 1 mole of this for every 1 mole of this, and then we've got these things right here. All right, so what I want to do is say, what would happen if we allowed the solution to completely evaporate? Let's evaporate off all the water that you would have when this reaction is done. So essentially what we're going to do is we're going to take away all the water. All right, and as it gets more and more concentrated, your sodium ions are going to basically start to form a solid when they start to form that crystal lattice. That's going to be the solid form of the salt rather than the dissolved form. And essentially what that's going to make is a pure crystalline solid, which is sodium acetate. All right, and sodium acetate, this is what it looks like when it's in its pure form. It's just going to be a white solid. All right, so essentially what you have when you are done with your reaction is a solution of that salt. All right, so if you ask yourself, what's the difference between what we have at the end of this neutralization reaction versus if we just took this compound right here, sodium acetate, and we just dissolved it in water? All right, would there be any difference? All right, and the answer is no. If you took that solid and you dissolved it in water, all you would have is a solution of those dissolved ions from that salt. All right, what do you have when you're done with this neutralization reaction? You have a solution of these dissolved ions. All right, so when asking what is the pH of this of the end product of this neutralization going to be, it is essentially the exact same thing as saying what would the pH of a solution of this salt dissolved in water going to be, because those solutions are going to be the exact same thing. So when considering what the pH of that solution would be, we need to take a look at the ions and just ask ourselves, would either of these be inclined to act as either an acid or a base? All right, and the thing that should stand out is acetate right here. And what is important about acetate is that it is the conjugate base of acetic acid. All right, and since acetic acid is a weak acid, all right, what that means is that its conjugate base would be, all right, so what that means is that its acetate is the conjugate base of a weak acid right here. And what we know is that if we know the Ka of that weak acid, we can figure out what the Kb is of this conjugate base. All right, and so and then from that we can go ahead and figure out what the pH of this solution is. All right, so sodium ion would not be inclined to act as either an acid or a base, so it's just going to be a spectator ion. All right, so we know that the resulting solution is going to be basic because it contains a weak base. All right, and hopefully that would should make intuitive sense that if you had equal parts of a weak acid and a strong base, that these guys are not equal in terms of their strength. And you would expect that the resulting solution should be more towards the basic side because it's a strong base with a weak acid. All right, so how would we go about figuring out what the pH is of that resulting solution? All right, so the first thing that we need to know is how much of our weak acid and weak base did we have when we did the neutralization. All right, so I'm going to give this information here. We're going to have 1 mole of this dissolved in 500 milliliters, 1 mole of sodium hydroxide dissolved in 500 milliliters. And from that, we can figure out the amounts of this right here in the resulting solution. Okay, so the amount of this ion right here would be 1 mole, and we could figure that out just from basic stoichiometry. If we had, so there's a 1-to-1 ratio right here that would create one of these right here, and since we started with, and these are added in exactly what you consider stoichiometric amounts, meaning there's exactly 1 mole of this per 1 mole of this. There's not a limiting reagent because you have the perfect amounts for a 1-to-1 ratio. All right, so that would give 1 mole of this right here. All right, and it would be dissolved in 1 liter of solution. All right, and that's because the resulting solution, you would add up the volumes of the solutions that got mixed together. That's where the 1 liter comes from. So we could figure out that the concentration of this in the neutralized solution would be 1 molar, which is not exactly true because of the following reason. And that is, when you have this right here dissolved in water, remember it's going to be a weak base. So some of that material has the ability to abstract an H+ from water to make its conjugate acid, which is going to be acetic acid. All right. So even though we're saying it's 1.0 molar, it would actually be less than that because some of it gets converted to its corresponding conjugate acid. All right. So how are we going to figure out what the pH of this solution is? Well, first of all, we need to know something about the pKb of this solution right here. All right. So the way we do that is we take advantage of the fact that we know what the pKa of acetic acid is. Therefore, we know that the pKb is going to be whatever that is, -4 or 14 minus that. All right, because remember that the pKb of something plus the pKa of something always have to add up to 14. All right, and that's essentially comes from this relationship right here. So therefore, we can calculate what the Kb of acetate ion is. All right, so what we're then going to do is the same type of approach as if we just said, what's the pH of this solution? Almost exactly in the same way if we just said starting from this salt. All right. So in doing that, we're going to do this with the same start, change, end chart that we've done before. We're going to assume before any reaction is started, all right, this is what you would have of this, and we would have none of this. All right, but if we allow this reaction to proceed, all right, the amount of your acetate will go down by a certain amount, and the amounts of these will go up by certain amounts. All right, so you could calculate an expression for the ending concentration, and then what we could do is we could set up our standard Kb expression. Remember, a Kb, what it's equal to is the concentrations of these guys in the numerator, the concentrations of this in the denominator. Remember, in that expression, we don't express the concentration of water. And we could substitute in for what we mathematically figured out those to be. And this right here comes from our Kb. And we could calculate x. All right. And remember, this is that situation where you assume this right here is the same thing as 1 because the amount of x is so small compared to the original concentration. All right. So from that, remember what X stood for. It's the concentration of hydroxide. All right. So therefore, we could calculate a POH. All right. And then from the POH, we could calculate a pH. So what this indicates is that the pH of this resulting solution would be 9.38. All right, which means it's going to be slightly basic. All right. And that should make sense because when you're neutralizing a strong base with a weak acid, the resulting solution should be on the basic side of things. So we're going to do the same thing in the next video where we're going to kind of switch things around, where we neutralize a strong acid with a weak base instead of a strong base with a weak acid.